Hi everyone, welcome back to the Heterogeneous Parallel Programming class. This is lecture 1.6, Introduction to CUDA. We will be discussing the kernel-based SPMD parallel programming. The objective of this lecture is to help you to learn the basic concepts involved in a simple CUDA kernel function. How do we declare a kernel? How do we use built-in variables in a kernel? And also to review how we can use a map thread index into data index. Here is a very simple example of how we can declare a CUDA kernel. And this is the vector addition kernel that we will eventually be launching from the host code. There are several important parts in this kernel. The first one is the keyword. Every CUDA kernel function needs to be preceded by underscore underscore global underscore underscore. And this signals to the compiler that the function is a kernel function. The actual header of the function is exactly the same as any other traditional C function. So we have the name, in this case, is back add kernel. And it's just a name that we happen to give to the kernel. And it's followed by all the parameters that it is expecting from the caller. Within the kernel, we will be able to use several built-in variables. The variables that we have shown in this code example are threadidx.x, blockdim.x, and blockidx.x. These are all built-in variables that are initialized by the hardware so that every thread can access these variables. And depending on the thread index and block index, every thread will have a different combination of the thread IDX and block IDX values. So that's why we will be able to assign a different value to the I for for different threads. And we already have gone through this concept in a previous lecture. Finally, we can use I as a data index to access the input data. So in this case, we'll be using I to access one A element, one B element, and write into one C element. We're going to come back and discuss the if statement, why we need to test what if I is less than n, n is the number of elements in the A, B, and C vectors. This slide shows the kernel launch code in the host code. In the previous lecture, we talked about the allocation of memory, copying data to device, and then we say that we're going to present the kernel launch part in this lecture, and this is where it happens. So we're going to change the second part of the vac-add function in the host code into a kernel launch. The kernel launch is very similar to any C function calls. So we still have the C function name. So this is the vac-add kernel. So this is just the name that we assign to the kernel. But between the function name and the parameters that we were given to the function, we also need to supply a configuration parameter set to the kernel. So we actually have two configuration parameters. The first one is the number of blocks in the grid, and the second one is the number of threads in a block. So what we're saying in this particular statement is that we want to have 256 threads in each thread block. And we want to have n divided by 256.0 and with a ceiling function number of blocks in the grid. So what's happening here is that whenever we generate threads, we want to have enough threads to cover all the vector elements. So if we have 256 vector elements, then it's a very simple case because it's 256 threads per block, and we only need to have one block to cover all the 256. So we will have 1 and 256 as our configuration parameter. So if n is equal to 256, we can simply divide it by 256 and we'll get value 1. If n is 512, it's also simple because 512 divided by 256 is 2. So 2 thread blocks will be perfect for covering 512 elements. The case that is much more complicated is when n is not a multiple of 256. Let's say if n is 1,000. When we divide 1,000 by 256, we get 3 point some fraction. And this gives us a situation where we don't have a perfect multiple of 256. So in order to have enough threads to cover 1,000 elements, we actually need to generate 4 thread blocks. And so that the 1,024 threads altogether will give sufficient coverage to 1,000 elements. But then we will end up with 24 threads that are extra. So in order to always generate enough threads, we will divide n by 256.0, and we generate a floating point number, which is 3 point fraction. And then we would take the ceiling function to be able to round up to 4. So this ceiling function ensures that we always generate the next bigger integer of blocks that will have enough threads to cover all the elements in this vector. The reason why we use 256.0 is because we need to make sure that we generate a floating point number, and that floating number will be rounded up. If we didn't use 256.0, but rather if we use 256, the division will be done as an integer division. So 1,000 divided by 256 as an integer division will actually generate a value 3. And then the ceiling function will not be able to take it up to 4. So this is one of the ways to ensure that we can always have enough threads. Now going back to the previous slide, when we launch, let's say, the kernel to process 1,000 elements, we will have 4 thread blocks, and we'll have the last thread block will have threads that will cover up to element element 999, which is the 1,000th element, because the elements start from 0. However, we will have 24 threads where the I value is going to be greater than or equal to 1,000. And these threads really do not correspond to any real elements of A, B, and C. So we don't want those elements to do anything. And in fact, if they try to access memory, they can actually corrupt the memory contents. So what we want to do is we want to be able to test whether the I value for for the thread is actually less than or less than 1,000. For only those threads that succeed in this test should do the element addition. So this is the reason why we need to have this check, and this is commonly referred to as boundary check, and it's actually testing whether a thread is supposed to be processing an element within the boundary or outside the boundary. So whenever the thread corresponds to an element that is outside the boundary, then the thread will not be doing anything in the computation. This slide shows 2 additional concepts for the kernel launch. The first one is we actually can have 2-dimensional or 3-dimensional grids and blocks. So the particular method that we showed in the previous slide only works for launching 1-dimensional grids. So each of those parameters are actually an integer value. Here we show that a general method for launching a grid of 2 dimension, 3 dimension, or in some cases 1 dimension. So now we need to declare 2 dimensional variables. They're of type dim3, and dim3 is available in the CUDA header file. And dim3 only means that a variable has 3 parts. Each part is an integer value. And we can initialize the variable with the syntax that we have here by having the variable name followed by parentheses. So the first value will initialize the x value, the second value will initialize the y value, and the third value will initialize the z value. And in this case, because we're using a one-dimensional grid, we only need to initialize the x values of both the dim grid and dim block. These variable names are of your choice. You can call them anything you want as long as you use them in the right position of the kernel launch. So in this case, we call dim grid the configuration that we want for the number of blocks in a grid. And then we have dim block as the number of threads in the thread block. So we can use this as a more general way of launching kernels. The second one is I'm actually giving you an alternative way to generate enough thread blocks to cover all the elements. Here, you can use n-1 divided by 256. In this case, 256 can be an integer. So this will give us an integer value, and then you will plus 1. And this will always give us the next bigger integer that will cover all the threads. So if we go back to the 1,000 example, you know what, 1,000 not divided by 1 will be 999. Subtracted by 1 will be 999. And if you divide it by 256, you will get 3. And 3 plus 1 is 4. And the most important case is that if you have, let's say, 256, what happens is 256 minus 1 is 255, so you will get a 0 from that division, but we add 1. So everything from 0 to 256 will give us exactly 1 block according to this division. So if you work out all these possibilities, you'll realize that this expression always gives you the exact number, the correct number of thread blocks that will be big enough to cover all the elements. So now let's put everything together. The kernel execution works as follows. In the host code, you have a host function, and then the host function can launch a kernel by calling the kernel function just like any other C function, but with additional configuration parameters. The configuration parameters need to be preceded by 3 less signs and followed by 3 greater signs. And so once we launch the kernel, we call that kernel function, then the hardware will generate a grid of threads to execute the kernel function. Every thread will be executing this kernel function. And the kernel function is declared in the CUDA program by preceding that kernel function declaration with a keyword __global__. So this allows the host code and device code to connect. And so that whenever the host code launch this kernel, it will generate this grid of threads. And all the threads in the grid will have these built-in variables, block IDX, block dim .x, and then thread IDX.x. And these predefined, pre-initialized variables will allow the threads to generate different data indices so that each thread will be processing a different part of the code, of the data. So now I'd like to just kind of summarize how you can treat all the function declarations in your CUDA program. We already talked about the kernel function and the host function. So there are really 3 types of functions in a CUDA program. The first type is what we have not talked about so far, which is device function. It's __device__. And this keyword tells the compiler that the function is going to be a device function that can be executed on a device, and it can be called by another function that is executing on the device. This kind of function is typically called by a kernel function or by other device functions. The second type is what we've talked about the most so far, the kernel function. So the kernel function is a very special device function. It can be executed on the device, but it can only be called by the host. This is really the gateway of parallel execution. When the host code wants to trigger any kind of parallel execution, it launches a kernel function. The third type is the host function. it can be optionally preceded by underscore underscore host underscore underscore. And these kind of functions are just the traditional C functions that will be executed on the host and can only be called from the host. So a few important details. Underscore underscore global underscore underscore declares that kernel function, and make sure that you remember there are two underscores in before and two underscores after. And the kernel function must return a void type, because these functions are special. These functions are really used to trigger parallel execution on the device. There's not a simple way to return a value. The question is which thread will even give you that value back. So that's why, to make it simple, the kernel functions must always return void. And the second one is the device, underscore underscore device underscore underscore, and underscore underscore host underscore underscore can be used together. And this gives you a function that will be compiled in both ways. It will be compiled into a host function. It will be also compiled into a device function. This way, the function can be appropriately used in both the host and device. And this is oftentimes used to generate useful utility functions that could be used on both device and host. Finally, if a function is truly only going to be a host function, then underscore underscore host underscore underscore is really optional. And this allows you to port a C program into CUDA very quickly, because all the original programs can just remain as with no keywords, and they will be assumed to run only on the host. And then you can gradually add keywords to the function declarations to make kernel functions and device functions, or make some of the functions both host and device functions. Now that we know how to declare a kernel, how to launch a kernel, and so on, I would like to tell you a little bit more about how a CUDA program is compiled. In every file, we're going to have both host function and device function. So the NVCC, which is the NVIDIA C compiler, will automatically identify all the host functions and kernel functions and separate them out into two compilation paths. The host functions will go through the host code path, where it will be further compiled by a host C compiler and linker, such as GCC, such as the Intel ICC, and so on. And the second one path is for the device function or the kernel functions. And these functions are compiled into a binary file format called PTX. And this is very similar to Java bytecode. At runtime, there's a just-in-time compiler that will take the PTX binary and generate the real ISA, instruction set architecture binary, for that particular device that you are using. So then both types of executables will be used for this heterogeneous computing platform, and the host path will be used on the host device, which is a CPU, and then the device binary will be run on the device hardware, such as a GPU. And this allows you to take a single piece of program with host and device functions and run them correctly in a heterogeneous computing platform. So at this point, we have finished the basic concepts of involved in writing a simple, basic CUDA program. And so I would like to encourage you to begin to take the lab tour. And the lab tour will show you the environment for you to write the CUDA kernels and so on for all the assignments. And then it will also show you how to get the instructions and how to submit your assignment. Once you finish that tour, I'd like you to encourage you to start the first lab assignment, which is the vector addition CUDA code. So this will help you to solidify your understanding of all the concepts that we discussed to date. For those of you who would like to learn more about the CUDA language at the introductory level, I would like you to recommend that you read Chapter 3 of the textbook. Thank you.